Okay, so for this lesson, we're going to combine the different exponent laws that we reviewed in the last lesson to simplify more complex exponential equations. So, if I'm using factors to explain why 6a to the 6 divided by 3a squared is equal to 2a to the 4, then I'm going to state that in its prime factored form, 6 is the same as 2 times 3, and then I have 6 a's. 2, 3, 4, 5, 6. I'm dividing this by 3 and a squared, or 3 times a times a, and then I'm going to remove the common factors. I have a 3 on the top and the bottom, an a on the top and the bottom, and another a on the top and the bottom. And all I'm left with on the top is I have the 2, and then I have the 4 a's, which means that this would in fact be 2a to the power of 4. So if I'm simplifying these things, then I can do the same process. I'm going to combine the coefficients. So 4 times 2 is going to give me 8. And I'm going to combine the variables. 8 to the 5 and x to the 5 and x to the 3 is x to the 5 plus 3, or x to the 8. For example B, if I have negative 7 a to the 8 times 6 a to the 12, I'm still going to multiply the coefficients first. Negative 7 and 6 gives me negative 42. A to the 8 times a to the 12 is a to the 8 plus 12, or a to the 20. When I get into these rational expressions or fractions, then I'm just going to divide the coefficients, or simplify if I can't fully divide them, and I'm going to combine the variables. So 20 divided by 5 is the same as 4. I'm going to look at this separately from the variable. Y to the 20 divided by y to the 5 is the same as 20 minus 5, or y to the 15. Now, when I get to example D, I can see that for this one, 30 divided by 45 doesn't divide out evenly. So all I can do is reduce this fraction. So 30 divided by 45 is going to be the same as, if I divide the top and the bottom by the common factor of 15, 2 over 3. And then I have b to the 14 and b to the 10, so I'm going to subtract them and be left with b to the 4. Now I could either leave it this way, or I could combine the b in the numerator. Either of these is an acceptable option. As we're going to see something more like this more frequently. When I get to example E, I start with my coefficients, 3 and 6, multiply to make 18. Then I have the a's, so I'm going to add them all up. 4 plus 5 plus 3. And those are going to combine to make a to the 12. When I'm doing the divides, like example F, typically I would start by rewriting this as negative 16 n to the 5 over negative 2 n squareds. Frequently I find that's just an easier way to combine the correct terms. So I'm going to combine the coefficients, and I'm going to combine the variables. Negative 16 divided by negative 2, the negative and negative are going to cancel out. 16 divided by 2 is just going to leave me with 8. And if I have n to the 5 divided by n to the 2, I'm left with n to the 3. When I get to example 2, where I have multiple variables, just remember I can only combine like variables. So if I have x to the 5, y to the 8, x to the 3, y to the 4, I can only combine the x's and combine the y's. So if I have x to the 5 times x to the 3, that's the same as x to the 8. If I have y to the 8 times y to the 4, I have y to the 12. When I'm dealing with rational ones, just like in the last example, I'm going to separate the things that I can actually combine. I'm going to just look at the x's and just look at the y's. So if I have x to the 5 over x to the 3, I'm going to be left with x to the 2. If I have y to the 8 and y to the 4, I'm left with y to the 4. When I get to example C, it's the same thing. It's just a more complex multiplication. So I look at the coefficients, -3 and -4. And those are going to multiply to make positive 12. I have b to the 1, b to the 3, and b squared. 1 plus 3 plus 2 gives me b to the 6. And then I have the c's. I have c to the 1 here. I have c to the 2, and I have c to the 1. 1 plus 2 plus 1 gives me c to the 4. For example D, it's another rational one, so I'm going to isolate the coefficients and isolate the different variables. 10 divided by 4 doesn't divide evenly, but I can divide both of those numbers by 2 and get 5 over 2. I have e to the 8 divided by e to the 4 leaves me with e to the 4. And I have f to the 12 divided by f to the 7, and I have f to the 5. Or I could combine these variables back into the numerator and say that it's going to be 5 e4 f5 over 2. Both those would be acceptable. For example 3, we're just adding the power of a power rules. So if I have 3x squared, then all in brackets to the power of 3, I need to remember that the exponent applies to everything in the brackets. So this would be the same as 3 to the power of 3, and then x to the 2 to the 3 is the same as x to the 2 times 3, or x to the 6. And 3 to the power of 3 is 27. X to the 6's. For example B, I have -2, a to the power of 2, b to the power of 3, and then it wants me to square it. So I'm going to apply the squared to the negative, to the 2, to the a's, and to the b's. A negative number squared is going to make a positive, so I'm left with positive 2 squared. A to the 2 to the 4, or sorry, a to the 2 to the 2 is a to the 4, and b to the 3 to the 2 is b to the 6. And 2 squared is 4. A to the 4, b to the 6. For example C, I'm going to combine on the numerator and denominator, and then I'm going to simplify across. So if I have x to the 3 times x to the 5, I have x to the 8 on the top. If I have x to the 2 and x to the 1 on the bottom, I have x to the 3. And then x to the 8 minus 3 leaves me with x to the 5. When I get to example D, once again, if I have the brackets and exponent outside, then that power of 3 is going to apply to the negative, to the 2, to the a, and to the y to the 3. So if I'm taking a negative and multiplying it a odd number of times, it's still negative. And then on the top I have 2 to the power of 3, and I have a to the power of 3. On the bottom, y to the 3 to the 3 is the same as y to the 9. And if I take 2 to the power of 3, I have negative 8a cubed over y to the power of 9. And that's my final answer.